Alright, so we're given what's a polynomial function here. Technically, we're only looking at this function for x values as they're defined on this interval. So basically, I've got two endpoints here on this function, one where x is -1/2, one where x is 4. To lead things off, we're going to find the critical numbers. So going back to our definition here and how we do that, we're going to look at where the derivative equals 0. We're going to look at where the derivative does not exist. So if we're going to look at the derivative, we need to take the derivative. F prime of x here equals, pretty simple on this one, 3x squared minus 6x. Now, using what we know about that definition for critical numbers, set up some categories here for when the derivative equals 0 and when the derivative does not exist. Now, on the does not exist side, really that's only going to pertain to the derivative when we've got some kind of denominator, right? Some kind of x floating around the denominator, because we know that portion there would not be equal to 0. So here, f prime does not exist is irrelevant. I don't see a denominator in that derivative I came up with. But the equals 0 side, well, we can do something with that. We can take our derivative here as we found it, set equal to 0, and solve. All right, looks like factoring's in play. We can take 3x out. Got x minus 2 left. Two factors set equal to 0. Solve each of those respectively. X would have to be 0 because of the 3x. X would have to be 2 because of the x minus 2. So if our critical numbers here are defined as, at least the way we've defined them, a number c, maybe to polish off this problem, we could say, therefore, c, our critical numbers, equal 0 and 2. And in drawing that conclusion, okay, we do have to be mindful of the domain of the original function. Right, there's a little warning label attached here. You have to make sure that these two numbers are included in the domain of the original function. Now, with the original function being a polynomial, the domain is all real, so this is not going to be an issue. But this is where we go back to what I was talking about before. You have to double check, take these numbers, plug in up here to the original function, and see that you get a real value back. If you do, then you're good. Right, so applying the same function over the same interval, we're going to find the absolute extrema. We're looking for absolute max, absolute min values. And we're able to do this because for this function, we do have a specified interval we're working on. We do have specific endpoints that we could look at if we graph this out. What you're going to do to find the absolute extrema. Anytime we do this, you need to start by finding the critical numbers. Okay, so if it doesn't ask you specifically to find the critical numbers, when it asks you an absolute extrema question, find the critical numbers first. Obviously, we did that. We know the critical numbers are 0 and 2. What we're going to do with those critical numbers is we're going to take them, plug them back in to the function. Notice the notation I'm using. It's function notation, not derivative notation. We're plugging back into the original function. Absolute extrema have to do with points that are on the original function curve. Now, the other thing we're going to do, because we are working on a specified interval here, we're going to take those x's at those endpoints, we're going to plug those into the original function. So we're going to take -1/2, plug in, and we're going to take 4 and plug in. All right, if we plug back into the original function, 0. 0 replaces the x's cancel out, we're left with 1. We plug 2 back into the original function. That would be 2 cubed minus 3 times 2 squared plus 1. So 2 cubes, 8. subtracting 12 there, right? So that's negative 4 plus 1, get negative 3 back. You plug in negative 1/2. Got negative 1/2 cubed minus 3 times negative 1/2 squared plus 1. We'll make a little room here to work that one out. Let's see, negative 1/2 cubed, that's going to be negative 1/8. Negative 1/2 squared, that's 1/4. If I multiply the negative 3 on, that's negative 3/4 plus this 1. The common denominator is going to be 8. Let's see, multiply 2 there, that's 6. Multiply 2 there, that's 8. This would be 8 over 8. F of negative 1/2 is going to come out to be what? Negative 1 minus 6, negative 7 plus 8, 1. It's 1/8. Then the other one we were going to find here was f of 4, right? So f of 4, following the same process, plugging in for the x's. Got 4 cubed minus 3 times 4 squared plus 1. All right, so we got 4 cubed, which is 64, minus 3 times 16, that's 48. So we're at 16, add 1, get 17 back. So when x is 0, value of the function is 1. When x is 2, value of the function is negative 3. When x is negative 1/2, value of the function is 1/8. When x is 4, value of the function is 17. We're looking at the values of the function now. We're trying to decide the absolute extrema, the absolute max or min. All you have to do now is say, all right, what's the biggest number I see that I got back? What's the smallest number that I see that I got back? Well, the smallest number I see is negative 3, right? So negative 3 would be our absolute minimum. We have an absolute minimum value of the function of negative 3 at x equals 2, or when x equals 2. Highest value we got back, down here, 17. Absolute maximum. Absolute maximum value of the function is 17 when x is 4. That's it. All right, if we're going to find the critical numbers given this function, then we got to take the derivative like we did before. F prime of x is going to equal, looking at my function up here, I've got a product. So applying my product rule, take the derivative of that x to the 3/5. That would be 3/5 x. Subtract 1 away, that's going to be negative 2/5. I take that, I multiply 4 minus x. I add x to the 3/5 multiplied by the derivative of 4 minus x, which is just negative 1. In the good old days, we left that alone, but now we got an application for it, so we need to simplify. As we simplify, locate where your negative exponent is. That's a good place to start. Got our negative exponent right here. As far as this x being raised to that negative exponent, I've got all this stuff here attached through multiplication. So I'm going to create a fraction out of that. And we've done this before. Right? You got your denominator of 5, I put that down here. Got my negative exponent, I put that down here, make that a positive power now. And if you recall, what we did was we took everything else, like the 3 and the 4 minus x, we left that on top. Now in the meantime, this guy over here, haven't touched that yet. I do know there's a negative 1 multiplied, so I might say minus x to the 3/5. Now we got this fraction situation that's playing out. We need a common denominator to put this all together. So normally the way these work out, I've got my common denominator right here. So I need to create a common denominator over here with this expression. So place that denominator down there, multiply same denominator to the top. And if you're doing these correctly, you're going to notice something happen in that numerator. What ends up happening here, as we put this all together over our common denominator of 5x to the 2/5, well, we've got our 3 times our quantity 4 minus x here, right? Let's go ahead and distribute that out. Make that 12 minus 3x. And as I was saying, you know you're doing this correctly if this second piece here, all these rational exponents go away. Right? What's the rule? I take x to the 3/5 times x to the 2/5. I'm supposed to add those powers, right? So if I add those powers, you get 5/5. You get 1 back. That's supposed to happen. Okay, we're supposed to have situations happen where these rational exponents become something nice and clean to work with. So you've got 5x to the first there. If you collect your like terms, derivative comes out to be 12 minus 8x over 5x to the 2/5. Got the derivative. To find the critical numbers now. Looking at where f prime equals 0. Looking at where f prime does not exist. Where f prime equals 0, since our derivative comes out to be this rational function, all we have to do is take our numerator, 12 minus 8x, set that equal to 0 and solve. If we do that, we've got negative 8x equal to negative 12. Divide by negative 8. Got 12 over 8 as the negatives cancel, so that's going to be what? 3 halves if you reduce. Potentially one critical number, 3 halves. Does not exist side. You got a denominator present like we do here. Take that, set it equal to 0. So 5x to the 2/5. Set equal to 0 and solve. Well, if we got to be real over the top about this, we divide both sides by 5, which hopefully you don't need to do, but you do that. You're now in a position where you're saying, okay, what to the power of 2/5 gives me 0? Well, that would be 0, of course. To make it official, to say, hey, we found the critical numbers, therefore, C, standing for those critical numbers, would equal 0, 3 halves. With the disclaimer that 0 and 3 halves are in the domain of the original function, and how do you know that again? You take those numbers, you plug back into the original function, you see that you get real answers back. And if we did that here, plug back into the original function, 0 and 3 halves, you would find that you do get real numbers.